Environment in which a robot is expected to work in can be either static or dynamic. Like a static environment is one where the goal and the obstacles are in fixed locations. But a dynamic environment, the goal and the obstacle locations can change as time passes. This gives a few unique problems in path planning. And say, for example, if we use a regular path planning algorithm, what the path planning algorithm does is it plans a path to the goal for the robot, and then the robot follows this path to the goal. Now, in a dynamic environment, the goal can be in motion. So what we could end up doing is the robot would plan a path to the goal, but by the time the robot reaches the location where the goal is supposed to be, the goal would have moved off, since it's a dynamic environment. So this could lead to a situation known as tracking, where the robot simply follows the goal around the environment, not being able to reach it. One possible solution for this is to predict the location where the goal would be, and then plan a path to that location so that the robot will be able to reach it along with the goal. This is in essence what our proposed approach does. It predicts, using the information given to us in the description of the world, it predicts the location of the goal and the obstacles at various times, at various time intervals, and then plans a path to where it could possibly reach. The best approach to do this would be potential field approach, where we assign attractive and repulsive potentials to the goal and the obstacles, and the robot simply follows the path it would take if based on the forces acting on it. It would be repulsed by the obstacle and attracted towards the goal. Now, there are a lot of functions many functions that we can use to model the attractive and repulsive forces. The main issue is to avoid the local minima and maxima. So the best function to use would be a harmonic function, that is a function that satisfies the Laplace equation. Such a function would not have any local maxima and minima. So all the robot would have to do is to follow the path of negative gradient provided by the equation, and it would reach the goal while avoiding all the obstacles. Now, this is the temporal potential function that is used by our operation. Consider, for example, a robot at location x, y at time t. So let's say it has the following options available to it at time t plus 1. It can either stay at its present location, or it can move a location forward, backward, left, or right. So the potential of that location, which is in essence the probability that it would collide with a obstacle if it sets off at a random walk from that location, is essentially just the average of the potential of the locations where it could be at time t plus 1. This is in essence the temporal potential function. Now we shall look at information to be provided to it previously, that is the potential value curves. These potential value curves are essentially the values that the starting point potential takes for various obstacle densities and look-ahead value limits. Now, the way the potential value curves are calculated is we take a set of randomly generated worlds of different obstacle densities. We set different look-ahead limits, and we try to calculate the potential, set the goal at different look-ahead limits, and calculate the potential value of the start state if the goal is at that look-ahead limit. This gives us a set of curves for each and every obstacle density. The curve is unique for every obstacle density. We just generate a set of potential value curves for various obstacle densities. These need to be generated only once. After that, every time the program runs for a new world, it just can reuse these obstacle density curves to calculate the path. The next step is to identify what look ahead we need to use. If we use too short a look ahead, then the robot might not be able to find a solution. If we use too long a look ahead, then the robot might take too long to find the solution, which it need not waste time. The first step to that is to find the shallowest goal, that is the first reachable goal. It might not be the best goal because the first reachable goal location might be surrounded by obstacles, but we need to find out what is the shortest time in which the robot can reach the goal. We do this by using forward chaining. This simply uses graph connectivity to find the first reachable goal. The depth to which we traverse in the tree gives us the time taken to reach the shallowest goal. Now, the next step is to estimate what look ahead time to use. Though the graph connectivity gives us the first reachable goal, it might not be the best goal. In this case, we are using the probability of a random collision taking place as the performance measure. So to estimate the look ahead time needed, we take that potential value curve which were calculated previously, and we compare the values of the time taken to reach the shallowest goal with the potential values that are necessary at the same look ahead limit, and we find out whether there is an advantage in incrementing the look ahead value. If we can find out by what amount to increase the look ahead value, we just increment the time taken to the shallowest goal with that, and that gives us the new look ahead to use. Once we determine the look ahead that we need to use, the next step is to extend the world in the third dimension, in this case time, and then calculate the potential values for all locations. So what we do is, in this case we are assuming a two-dimensional world, and that's extended into time as a third dimension. And then what we do is, for every point in time, we calculate the goal and the obstacle locations, and we populate the grid with it. The top layer of the grid is then given a boundary condition where it's given a potential of 1. This essentially lets the planner know that it tries to find a solution by the look ahead time. After this, we use the temporal potential function that was previously shown to calculate the potential of all locations in the grid world, working from that point onwards. Of course, in this case, every obstacle location automatically gets a potential of 1, and every goal location automatically gets a potential of 0. Using this, we work our way down from the top to the bottom till all locations in the grid are populated. After that, the way the robot finds a path to the goal is very simple. All we need to do is simply follow at every time start from the start location. The robot just goes to the neighbor with the least value for potential. This will essentially plot a path for the robot that is the safest path to take, avoiding all the obstacles and reaching the goal at a location where the odds of meeting an obstacle are very low. Now, during the entirety of this process, if at any point the dynamics of the environment, that is the velocity of either the obstacle or the goal, changes, all we need to do is restart the process, which shouldn't take too much time, since all these calculations are one time. Now, a few other experiments were done to see how various factors affected the potential values. In this experiment, what was done was a randomly generated world was taken, and the potential value of the start state was calculated for various look ahead times. Now, as soon as we reach the first look ahead time, as soon as we reach the goal, first reachable goal becomes visible, the potential value of the start state starts to drop sharply. but once we reach a certain look ahead time, the potential value does not drop any further. So what this essentially tells us that it is no point in just setting a large look ahead time from the get-go and starting off the algorithm, because we'll simply be wasting resources. In this case, for example, setting a look ahead time of 400 or 450 time steps wouldn't have done us any good, because the look ahead time of just 50 time steps would have been enough to get the solution, to get to a solution with the same risk as that which would have reached for 450 time steps. In the next, yes. In this experiment, we can see that the look at time. There is also a point. There is also a factor involved, is that the potential of the start state depends on the time taken to reach the goal. Like in this experiment, the goal was set at the look ahead value, and it was ensured that the goal would not be reachable at any other look ahead value. So this essentially shows us that as the longer we take to reach a goal, the more the potential increases. In this set of worlds of various sizes but with the same obstacle density were taken and the potential of the start state calculated. Now what this shows us is that the potential value curve, that is the potential that a robot having, this is also shown by this graph, which was we simply took a world of a fixed size and varied the obstacle density and calculated the start state potential. Though the goal was at the same location, as the obstacle density increases, the potential of a random obstacle collision also increases. Now in this experiment, the goal was set at a fixed location in time, and we ensured that and we set off the algorithm just to see if it would reach the goal. Even though the goal was in a location where the obstacle collision probability was high, the robot plans a path to it. However, if a better solution is found, in this case better of course meaning one with lesser probability of obstacle collision, then the robot ignores the previous goal, which even though it is in a shorter, it's quicker to reach, and it prefers the safer one. So in essence, the robot prefers a safer goal to a quicker goal. So in conclusion, the algorithm, if a solution exists, will find it. But if a better solution exists, better in this case again, the safer solution exists, it will try to find the safer solution rather than the quicker solution. And potential value recalculation is very simple, because all you are essentially doing is averaging out values. And within a given look ahead time, the temporal potential function ensures that it will find the best possible solution in that look ahead time. Now future possible work would be to figure out a more robust method for finding out the look ahead time, since the current method is approximation, and to find a way to update the potential values on the fly when the dynamics changes to avoid recalculating from scratch. MATLAB implementation of the method is available at this address. Thank you for your time.
Thank you. Questions?
Yeah.
Your method will have the trap situation.
I'm sorry?
Trap situation for commonly occur in the potential field method. Trap.
Oh no, since we are using the function that is essentially